So let's continue. Oh. Ah. So let's continue with the augmentation, and that is kind of the aid when you have too little data and you want to still shake up a bit more. And what you can do is actually to modify your data set with different transformations. And typically the transformations you do are shifting, moving it around, zooming, rotation, intensity, normalization in different ways, scaling, color changing, shearing, and so on. What you can also do is to add noise and blurring to introduce more, say, acquisition type changes. Some examples you can have is this is retinal blood vessel scans. And the original was like this. You can see the grid, how it was modified, and here you see also the labeled blood vessels in this database. These images come from the Drive database, which is open. I think you need to log in to get access, but it's open. These images were prepared by my former master student. And what you can do is, one is some kind of elastic modification, where you can see that this grid is a little bit elastically modified. You can also rotate to get different orientations. You can also play with the zoom. So there are different ways. In this case, it was also an asymmetric zoom, so a little bit less in one direction than in the other. And this kind of modifications is what you can do to enhance or make your dataset a little bit bigger and letting your training see more variations. One example is that if you just have people standing straight up, you're not able to see the same thing if you just tilt it a little bit. There are, of course, also limitations on what kind of augmentation you can do. And the first one is actually physics. And in some cases, even geometric. But let's start with the physics part. There is a given range of values you can have on in the image to still have a physical meaning. In the medical imaging, we have the Hounsfield units. Organs, they have very well-defined intervals in where the gray levels are. And if you change them, you actually change the diagnosis. So you can't change the intensity values very much. And the other one is also you can't flip, because that is also sometimes not realistic for the type of samples we are looking at. So, for example, the head should maybe always be on the top to make it realistic. Then it's also how much you can distort. You should, of course, still be able to recognize the features, so you can't distort it beyond recognition, because then it doesn't really make sense to use the data. And the sanity question is if the distortion is within the natural bounds. No people are 3 meters tall and also not 10 centimeters, so that is not realistic. For doing this, here comes a little bit of code. We have in the TensorFlow Keras environment for machine learning, there is this image data generator, and it has a lot of parameters, and this is the help page generated for that. There is also an augmentation demonstration, but if you type just help on this data generator, you get a lot of information of what you can do. And to make this a little bit more compact, We can see here what kind of features we want to play with. This is a bit small, I would say. So let's see if I can make it bigger. No, I'm not allowed to. That's strange. Oh, sorry, that one. So, then you can see. So here we have that you should look at different centering approaches, some whitening, rotation range that you can only rotate plus minus 30 degrees. You can only shift 25% in each direction. You cannot do too much shearing and so on. So with this you can program how much you allow these images to be modified. And now I need to go back in the size. So let's go back to the MNIST. Here we have a little collection, numbers 1 to, it's not really 1 to 9, all of them, but anyway, here we have the top row, we have some images and then some numbers, originals, and then we do augmentation based on the settings I had on the previous page. And here you can see that the 2 here is a bit scaled. This one was moved, this one was rotated and moved, this one was stretched and moved, and so on. So there are different augmentations in these lines. And that gives us more variety afterwards when we use them. And still, it's always associated with the same label. Then we can look at the CFAR dataset, which has a lot of different categories. And we have here, so automobile, animals, so different machines and animals in this case. And let's run some augmentation on it. And looking at the images, these are very small images actually. So the top line here gives the originals. And you can see, for example, this one made a little bit craziness because there was a mirroring effect allowed. So the horse is mirrored top down and sideways, and that makes it a little bit unrealistic image. So that is something you have to check if you start doing augmentation, to check that it actually augments in a reasonable way. Also these birds, this one is a very fast bird, it looks like. It doesn't really look like a bird, so you have to be careful that you augment in the right way. What is tricky in this case is also that these CFAR images, they are very small, so you don't have many pixels to play with, and that also makes it harder to do this augmentation. So let's move on from the augmentation into baselines, and a baseline is an algorithm that we use as, say, to test our development against. It's an algorithm that is very simple, easy to implement, and also the fundamental model of what you want to do. It should also illustrate the problem. By no means it needed to be high performant in any way, but it should at least demonstrate what you can do. So it's kind of a worst case scenario to test how good are we. So we need to have some example, and in this case a classic demonstration baseline is we have a model that is more than 99% accurate for predicting breast cancer. And the algorithm is very simple, is saying, do I have breast cancer, given the number, age, weight, and race? And the algorithm always responds no. And given the probability of breast cancer, this one is always right. Because, you can see here you have an accuracy of 99.91%, but it still doesn't grasp what you actually are looking for. So it's not really a good baseline. What we can do, what we have in, for example, scikit-learn, we have a dummy classifier, and the dummy classifier you can tell to do different things, and in this case we can say the strategy should be most frequent. And if we do a fitting on some data, we have 1, 2, 3 here, and they are healthy, 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 and cancer. And then we train it, and we get this little box as an output that it's trained. And if we run the same some values on this classifier, we have 0, 1, 2, 3, and 100, and the prediction is all the time healthy. And that makes sense, because we now asked for most frequent, and the most frequent is healthy. And then we more or less back to this case is essentially also the most frequent choice. It's not good, but it's something to start testing against. So let's try this dummy classifier on the MNIST data, where we have our numbers. There is also the histogram on how often or how frequent these different numbers appear. And you can probably already, by looking at this histogram, already get an idea what is going to happen. But let's look at it. So let's train our model based on these images and the labels. And we got now the most frequent. And if we test the prediction at basic test, we see all are ones. That is, everybody are predicted to be a 1. And well, that is to be expected now, because we had most frequent, and the 1 is the digit 1 is the one that is most frequent in this data set, so everybody are supposed to be a 1. And well, that we see in this histogram again. Another baseline would be nearest neighbor. That is a supervised classification algorithm. And in principle, what it does, it has a training data set with a lot of points. And when you have these points and get a new one, it computes the distance to all these points. And the point that is the closest is the one that tells which class you have. And we can do it, of course, with different number of neighbors. So in this case, it was the only one neighbor, and it gave you this segmentation line between the two classes. You can also do it with several points. So you can, in the second case, we had 9 neighbors which are compared with, and you take the majority class from these 9 neighbors. The first thing you can see when you increase the number of neighbors is you have a more smooth separation line. You can also see that you have some red and blue dots in both classes. So it's, say, more robust in that sense. So let's do the MNIST again and see what happens. We train with these images, and we have only one neighbor in the training. And what's happening is the prediction comes out like this. We see these numbers, and what we get out of this baseline is actually a pretty good result. Perfect hit. So what do you imagine would have happened here? It's fantastic that we get everybody the same. The problem we have is that we used exactly the same data set to train and to test. That is, we have a perfect match, and that is not really what we wanted. So if we instead would start testing with taking out, we trained with one part, and we tested with another part, and then all of a sudden you can see that it's not that good. Sometimes it does good, but not always. So for example, here it's a 0, but it predicts a 3, so it's not really a good choice here. So it does, I would say, 50% right, 50%-ish. So it's at least a baseline for how good we can do, and then it's up to our next algorithm to perform better than this. If you're worse, then completely reject what you're doing and go back to square one. So when you do this kind of comparisons, you have to have some kind of metric, how good is actually good. And what we use for that, one tool is to work with the confusion matrix, which in the simple case, when you only have two classes, gives us this little matrix here. And what we have is the actual true and false in the classes and the predicted. Ideally, you should have only values along this diagonal. So the actual true should be equal to the predicted true, and the actual false should be the same as the predicted false. That would be the ideal case. If you have something going out in the other case, that you say it's true, but it should have been false, then you land in this position. And if you do have actually a true, but predict false, then you land here. And then you can also see that there is maybe a tendency to do more predicted false or more predicted true, so false predictions in those two. And then with that, you can also see if there is a bias in your algorithm. Looking at the numbers, we can see this is pretty dark now. Can I take this one? Oh no, it's motorized. Okay. Anyway, I hope you see at least there are some brighter boxes and darker boxes along the diagonal of this confusion matrix. And here what we say is the true label on the y-axis and the predicted label on the x-axis. And we can see some numbers, they reoccur. So for example, the 4 is apparently often confused with the 9, which kind of makes sense. They have often a similar shape. The 7s and 7 and 1, I would have expected that they would also do something similar, but apparently the 1 and 2 does some strange things. So from this, you can make conclusions about which are the combinations that are sensitive and which you may have to put some more efforts into. So, leaving the theory part and moving over to a way how you can manage your data and information, and that's data frames. I started already last week showing a little bit with data frames, and our workflow is that we do a lot of analysis, and at some point we start getting into a collection of features which are typically stored in some table. Tables can of course be used in Excel, so in spreadsheets, but another way, if you want to continue working in the Python environment, is to work with these data frames, which is a kind of a spreadsheet-like thing. You can actually also put images in the data frame if you like. So that would be another option, that you actually have the different steps, or you have the original image and the final image, and then some statistics around it. And what we have, if we have lots of feature data that we then extract in these tables, and like in the spreadsheet, you can do counting in here, you can do statistics, you can also do selections, filtering out. If I have, I want to look at, for example, all the females and with shoe size 42, then I can select those and do statistics on those specifically. And it's pretty easy to do it here. And you can also do transformations and visualization, like plotting the contents of these tables. And what we have is different ways to organize the data. You can actually program up the whole thing, that you have a lot of arrays or lists of different structures or dictionaries, but this is usually very unpractical and hard to redesign, and of course then you land into a lot of errors, and that is why we use these data frames. So in principle, what a data frame is, it's a data container, and it's organized into columns and rows with the similarity to a spreadsheet. And it takes actually any data. So as I said before, you can also even take images into these cells in the data frame. And with that, you can apply the different filters, sorting you can also do. I didn't mention that. You can do arithmetics on the columns and compute statistics. And an important thing is also that you can read and store into files and databases. So there are connections to spreadsheets, there are connections to SQL databases, and that makes it very easy to get in the data once you want to work with it. So in your processing workflow, you may produce a lot of table files, and those table files can be then read into the data frame. There is a pretty good documentation for these data frames, and there is the main documentation, and then there is even getting started with pandas on their webpage. And these are pretty good tutorials if you want to work with these. And but still, I'm going to show you a little bit how it works. The first thing is we want to create a data frame, and that can be done from a dictionary in Python. It can be done from a data file, and it can also be done from NumPy arrays and lists. The first step is that we need to import pandas, and typically it's replaced by the abbreviation PD. That is what kind of the convention is. And let's say we want to read in from a spreadsheet file. In this case, it was a CSV. You can also take Excel files. If you have an Excel file, you can specify also which sheet you want to read. But CSV stands for comma-separated values. But it's pretty flexible. You can also don't have to have commas. You can have any separator you want. So here we do a PD read CSV, and then I take the file. And in this case, I want just to look at the table, and I take a sample with 5 rows. And when I do sample, it takes a random selection anywhere in the data frame. And then you can see what information is here. I think this was some kind of bone mechanics data set with phenotypes, etc. Actually, I don't know exactly what it's in here. And then if you want to save it, then you just do the data frame variable .toCSV, and then you can save it like this. So another way is to create it using a dictionary that is a mapping between some kind of value or label. So a dictionary is a mapping between some label and a value. And in this case, I create a dictionary with position, :0, and sign is just a sign function, and its value. And it's added to a Python list here with the help of append. And with that, I get then a long list of small dictionaries. And this list of dictionaries can be added to the data frame. And if we look at head 5, head means it takes the first 5, in this case, 5 rows from the table. And here you can see that the position is 1, 2, 3, 4, and the sign values, I actually don't know if they match, but I assume that it does the right thing. Yeah, so this is how this table is generated, and now from here on, we can start doing funny stuff with this data frame. An alternative is that we instead make a different way to wrap the dictionary, is that we create two numpy arrays or lists, whatever you like. They need to have the same size. And then we just say that the first element of the dictionary is the position, and it gets the X position array. And the other position has the sign, and that gets the array of the sign values. And these are then added in the data frame. Looking at the head, we should have exactly, no, we don't, because we have a linspace here. Okay, so we get different values than before. But anyway, we get the sign values from here. What we can do is then working with columns, like in Excel, you can also create new columns and fill in new values. And that's pretty easy to add a column. We just do data frame and telling what the column should be called. And then we do some operation on one of the other columns. In this case, I took it on the position, and compute the cosine of the position vector. Then the next column we add is the sum, and then we can take two columns out of the data frame and sum them, and that is our sum. And the next one is to do some kind of thresholding. We just say if it's positive, that would be that the sign column is greater than 0, then we get a true or false, and then we have a Boolean variable in that one. And if we look at the head, the default value of head is actually that you have 5 lines, so we don't even have to write that we want 5. And then we see here what we got. We get the sum of the two, we get the cosine, we got the sum, and we got the positive. So now we have already built up, using different columns, we have built up an extended table based on this data. And now, if we want, we can start doing some selection. So we filter. We can see that we create a new data frame where, for the cases where the df sign is greater than 0, that creates the data frame 2. Here we see if we select the lines where positive is true, and then we can look at the head, df2 head, and then we see that all the values here are positive for sign, and the positive column is also all true. So that was the criteria. So by doing this, you can really select which parts of the table you want to focus on in your calculations. Then sometimes you get strange names on your columns. If you remember back on the phenotype data set, maybe the names of the headers, they were a bit cryptic and you want to rename them. That is possible. So let's create a little data frame here. We have 2 columns, A and B, and that wasn't really ideal, so we want to rename them. That is done using here a dictionary where you do the mapping from the old label into the new label. And in this case, A and B were turning into hey hop. And after this operation, you get the new column names. So that is an option if you want to do it. You realize that something was not really correct, or in the way you wanted it. What you can do as well is to compute some statistics on the data frame. You can look at, you can compute for all the columns. You can compute the average value, standard deviation, min, max, and median. And for example, if we take the mean of the DF, you get for all the columns, you get some value. And interesting is that for positive, which is a Boolean column, then it actually computes the value of true and false as true equal 1 and false equal 0, and then you get the average of that. Looks like I've missed some kind of separator here. So let's look at the next one. We can also summarize the statistics of a data frame, and we could of course compute for every one. We could compute the mean, standard deviation, etc., etc. But there is a command, as this is a pretty common operation. There is this df describe command, which actually gives you all this information in a nice table. So a convenience function, which is pretty good. It also even gives you the quantiles, 25, 50, and 75%, and the min and maximum values. So that's a quite convenient functions to have, at least when you start doing the exploration of your data. Then we want to do some kind of statistics on filtered data. I showed before that we can select parts of the data, and we want, for example, compute the standard deviation for the sign column, but only when the rows have greater value than 0 in the sum. So what we need to do is, first of all, select the sum, which is greater than 0. And then from that selection, we want to select the sign column and compute the standard deviation of it, and then we get some value. So the magic you have to do with the data frames is a lot of selection and find the right selections. Sometimes it can be a bit tricky, but you can get pretty nice results out in this way. And we can also do some grouping by helping with the group by and doing some aggregation with the help of that. So we want to group around the positive value, and then we want to compute the mean value of that grouping. And looking at the table then, we have the positive is true and false, and then we get, for the remaining, we get the positions in false and positions in true, and then we have all these for the sine, cosine, and sum. It can be pretty complicated grouping situations, and for getting the right thing, I actually recommend using some kind of LLM to, call it manual on steroids, because getting the right groupings is not always so easy, particularly if you want to dig around in the manuals. I'm not saying you should do full vibe programming, but it's a very good help to get the results out. And then, of course, if it's too cluttered, you can always reduce it a bit, and getting only the mean and variance for some specific columns. So you see the lines, they grow a lot, and there are a lot of combinations. What you need is up to you and your tasks, but there are a lot of ways to get around with these data frames. You can also do some plotting. Until now we used matplotlib, but the data frames actually also support some of the matplotlib functionality. Also Seaborn can work pretty well with these data frames. But if you just do a plot of a data frame, then you get all the columns plotted like this. May not really make sense always, so you have to do selections which column you want to use for the X and Y axis, or how you want to present your data. So for example here, I'm looking at just the sign column, and then you get that one. You can also do a plot of X for the sine column and Y for the cosine column and put that in another axis. And you can see that together they plot the circle, which would be expected. And then you can also plot the column cosine as function of the position. So that is also, so it's a bit different than this one where we just plotted the axis, and that one is plotting the position and the column. So you specify how they are connected together. You can also do different plotting types, bar plots, scatter plots, and so on. So it's then you can say here, you can add this command kind and say how the data should be plotted. And the question is when you should use these data frames. And sometimes it really makes sense, and other cases I would doubt it. So it really depends on how much data you have. So the raw images can be terabytes of data, and Pandas is not made for working with that. So that wouldn't be a good case. Also the segmented images, maybe, depends on how you have cropped it. Then when you come into feature data, then it starts making sense. And you can see here the plots are data size, which is going down, and the level of abstraction is going up. So in principle, the more abstract data you have, the more reasonable it is to put it into the data frame. The model itself, maybe not really, could be that you have model parameters that you put in the data frame for different cases. And then if you want to have really big data, then you may have to move towards the Dusk data frames, which then actually can also work against remote data sets and just giving you an interface towards that looks like Pandas. And well, that was end of today's lecture. So important is we really need good data, but the question is what is the good data and how we should prepare it. Then that there are many data sets. You can probably find data sets for any of your applications. For medical applications there is a lot, very specific and also more general. For the augmentation is our way to get around the fact that we not always get as much data as we would like to have, and then we can modify our data. Then going on, having the data, we want to start doing comparisons, how well our algorithms are working, and then we need some kind of baseline telling this is the worst case we can have, can we get better? And in the comparison, it's very useful to work with the confusion matrix, and that one can tell how well our algorithm is performing. And the last part now was a bit more technical about data frames, a way how you can organize your measured data, and also how to do some analysis on it and also do plotting. Next week, I'm going to talk about noise and filters. So then we are really going into the more classical image processing tasks. The first step, once you have measured your images, how you can improve the image quality to some degree. And also in some cases doing some analysis already here. And well, that was the end of today. Thank you.